When an algorithm predicts criminal recidivism, does it eliminate human bias, or does it permanently codify the systemic inequities found in historical data? As foundation models centralize hundreds of downstream tasks, an invisible failure in a single base model transforms into a systemic crisis across the public sector. Welcome to Wandt courseware, an AI-narrated video series unpacking the latest lectures and thoughts of Professor Adam Scott Wandt of the John Jay College of Criminal Justice in New York City. Traditional government software procurement assumes a static, rule-based product. You test the code, verify its logic, and expect it to perform predictably once deployed. Modern AI follows a different logic. These systems are dynamic and predictive, constantly shifting their behavior as they process new data inputs. Treating these evolving algorithmic models like static IT software is a severe governance failure. It leaves public institutions exposed to systemic risks that a one-time audit cannot catch. Safely governing AI requires public administrators to look past the user interface and understand the underlying mathematical mechanics. Our first step is breaking down the distinction between traditional causal inference and predictive machine learning. Next, we will analyze the unique architecture and the specific risks associated with foundation models. Finally, we will explore how the NIST Framework and White House guidelines provide a blueprint for managing the entire lifecycle of an AI system. Protecting civil rights in an automated world requires policy analysts to master technical literacy. Traditional econometrics focuses on parameter estimation. It seeks to isolate the causal effect of a specific variable to understand exactly why a policy leads to a specific outcome. Machine learning prioritizes a different goal: out-of-sample prediction accuracy. These algorithms leverage complex interactions between thousands of variables to generate the most accurate prediction possible, regardless of the underlying why. This diagram shows the transition. While a standard regression focuses on a single variable, a machine learning algorithm builds a high-dimensional web of intersecting data points. To validate this performance, the model partitions available data into separate training and test sets. This reveals the core tension of supervised learning, the trade-off between bias and variance. If an algorithm captures too much noise in the training data, it results in overfitting, a chaotic model that fails to accurately predict real-world outcomes. Engineers apply regularization techniques to mathematically penalize this complexity. This smooths out the model, allowing it to ignore noise and accurately predict outcomes in the separate test dataset. These algorithms are highly effective for resource allocation decisions, like identifying buildings at high risk of fire. However, they remain blind to the underlying causal mechanisms driving that risk. Public sector leaders face severe policy failures if they confuse predictive correlation with causation. Using machine learning to make policy changes that require causal knowledge will lead to ineffective interventions. Moving beyond basic supervised learning brings us to the massive scale of modern neural networks. The Stanford Center for Research on Foundation Models recently analyzed how these massive systems are changing the technical landscape. They identified foundation models, large-scale neural networks trained on broad, unstructured data that can be adapted to a wide range of tasks. These models exhibit emergence. These are unanticipated kids' abilities and behaviors that spontaneously appear only when the model reaches a massive scale. This architecture leads to homogenization. As seen in this diagram, a single central base model acts as the core for dozens of diverse applications, from natural language processing to reasoning tasks. This centralization offers flexibility, but it means any bias or vulnerability in that central node is automatically inherited by every downstream application. Homogenization creates a single point of failure. A flawed model can compromise multiple public sector services simultaneously, making these failures mathematically difficult to isolate or fix. We can see these mechanics in action within the high-stakes environment of the criminal justice system. Researchers analyzed algorithmic models used to predict flight and recidivism risks in pretrial release decisions. Theoretically, the consistency of an algorithm could reduce both crime rates and jail populations compared to the subjective decisions of human judges. However, evaluating these systems requires addressing the omitted payoff calibration problem. This diagram illustrates the data gap. We face selection bias because the court only observes the behavioral outcomes of defendants who are actually released. This is the counterfactual problem. We cannot observe what the jailed defendants would have done had they been freed. The study bypassed this bias by analyzing variations between strict and lenient judges, allowing for a rigorous comparison between judicial discretion and machine predictions. Algorithms can reduce human inconsistency, but their deployment forces administrators to make explicit policy choices. They must ensure the system does not simply automate the systemic inequities hidden in historical data. Because AI models exhibit emergent behaviors and data drift over time, traditional one-time software testing is inadequate for the public sector. The NIST AI Risk Management Framework provides a flexible guide for organizations to manage these ongoing risks. Trustworthy AI requires more than a simple pass-fail test. It must demonstrate validity, safety, privacy, fairness, and accountability. This circular loop represents the NIST Framework's approach. It integrates risk management into the entire lifecycle of an AI system through 4 functions. The map function identifies specific contexts and risks, while measure focuses on quantifying those risks. Manage involves allocating resources to mitigate risks, and govern establishes the organizational culture and policies that sustain the process. Algorithmic accountability under the NIST framework functions as a continuous administrative process designed to adapt to emerging model behaviors. These frameworks provide the structure for protecting civil rights in the era of automated systems. The technical companion of the White House blueprint for an AI Bill of Rights translates these principles into specific operational practices. It requires rigorous pre-deployment testing, including data quality assessments and validation against real-world scenarios. Agencies must conduct continuous algorithmic bias audits to ensure systems perform equitably across all demographic groups. Clear paths for human oversight are essential. Citizens deserve accessible explanations for automated decisions and functional fallback options when systems fail. Public administrators must avoid relying on proprietary black box algorithms that cannot be scrutinized by the agency. Technology can augment decision-making, but the responsibility for automated outcomes remains with the agency to ensure alignment with public values. Like, follow, and subscribe for more deep dives into emerging technology, digital investigations, and the ideas shaping our future. And remember, stay curious and want knowledge.